Yeah, so thanks for joining. I'm Thomas. I'm one of the co-founders at LocalStack. We build a local development platform for cloud applications, and we've recently opened up the platform for building extensions. And we've also been using Tinybird internally, so this is a nice match. And today we'll build a LocalStack extension that logs AWS API calls into Tinybird.
Okay, I'm Jordi, a data engineer from Tinybird, and let me do a brief introduction about what is Tinybird. Well, what we have tried to build is a serverless all-app database for developers, and we use ClickHouse underneath. And the good things about Tinybird is that you don't have to care about the infrastructure. Everything is based on SQL, and you can build a low latency API with 2 or 3 simple clicks. Also, we have a lot of built-in tools for developers that make really easy to ingest data and so on. And as well, I had to put here a catch phrase from marketing, and this is what one of our users says about us, and he says that we are like Kafka, ClickHouse, dbt, and Fast API all in one platform. I don't know, Thomas, if you agree with that bold statement.
Yeah, I think that's quite a good summary of what it feels like, and I think what's missing is that it just makes it ClickHouse makes it super easy to use all of those tools. It's not just all of the functionality of those tools; it's just integrating them in a very intuitive and easy to use way.
Well, thank you. I thought that the affirmation was bold, but you made it bolder. So
I'm a fan.
If you want to share your screen and start with the demo.
Sure. Yeah, I can share my screen. So I have a few just things to share about LocalStack. Maybe before we get into the weeds. So maybe for those who are not familiar with LocalStack, I'll briefly explain what it is and what it's used for. So the core of LocalStack is really, in short, an AWS emulator. So if you're building an application that uses AWS cloud services, you can run your application on top of LocalStack, and it will behave in the same way as if it would run in AWS. So LocalStack provides these emulated AWS services, and they speed up your development workflow because, first of all, you don't need to deploy your application to the cloud, which can be slow. You can just run it on your laptop. And you'll see later in the demo that also our emulated services just respond quicker than those in AWS. So, you can run your Lambdas or connect your SQS queue to your SNS topics and so on. And LocalStack is also useful for test automation. So you could spin up LocalStack in your CI environment and just run your test suite. And that really gives you the confidence that you can later deploy your application to the real cloud, where our emulated services are then substituted by the real AWS services. And I'm just going to give you a quick demo of LocalStack and basically how easy it is to use. So LocalStack comes with a CLI, and you can basically just run LocalStack start in detached mode. LocalStack comes packaged as a Docker image, and it's just spins up a Docker container with everything. So the only requirement that your computer has is having a Docker. And if you inspect Docker, you can see this LocalStack image running with a bit of network configuration. And now LocalStack exposes through the port 4566 an AWS endpoint, and you can point all of your AWS tooling to that port, and it should most of the services work out of the box. So I'm just going to demo this. Common tool is the AWS CLI. And I have something prepared here, which is just SQS, which is a queuing, managed queuing system from AWS to create a queue. And you point your CLI to this endpoint, and you run that, and it behaves in the same way as AWS does. So we have a small wrapper script for this, which makes it easier for you to work with the CLI, but it's just it just basically hides this here for you. And I don't know, let's send a message to that queue, for example, to demo that it it works, and you can receive messages from that queue now. Oops, sorry, that was the wrong queue. Place this here with the test queue. You can see like sort of this the services behave in the same way, and this is really AWS Local is just a drop-in replacement for AWS. And you can run also other types of, if you're building things with infrastructure as code tools. So let's say Terraform. We have a bunch of Terraform samples that run against LocalStack. And let's just open up something here, for example. So we have an example that uses S3, the storage system, together with SQS. And I'm not going to go into details. Terraform, if you're building things on top of cloud providers, you're probably familiar with it. It's just a declarative way to describe your cloud infrastructure. So here we're describing this queue, we're describing an S3 bucket, and we're describing a notification configuration that shows that sends a notification to SQS if you create something in this S3 bucket. I'm just going to run this. Terraform apply. Just apply this configuration, and as I said, if you're familiar with Terraform and AWS, this takes a lot longer against a remote cloud. And we can now go back to maybe list queues, and you'll be able to see this queue being created. And let's see, let's also check the buckets of this test bucket. And what I'm going to do is I'm just going to copy a file into this bucket now. So just this script in this directory. It doesn't really matter. I'm just going to copy something in this bucket. And now if I receive a message from that queue, we should see this event notification from S3. So this is the SQS message, and the body contains the event notification from S3. So you can see that the service connections or the connections between services, AWS services, works as well in LocalStack. So you can connect, you can trigger a Lambda from an SQS message, for example, or any type of integration that works in AWS also works in LocalStack. Okay, so this is just basically a brief demo to show you that LocalStack behaves in the same way as AWS does. And people are often skeptical when we show them this, and they're not familiar with LocalStack. Like, how does this even work? How can you do all of these things locally? AWS is this huge company that has all of these resources to build this cloud system. How can we, as a small company, keep up with this moving target that is AWS? And we wrote a blog post about this, explaining how we maintain parity between LocalStack and AWS, the way that AWS services do, and just the tooling around that we built around keeping parity with AWS is explained in this blog post. So if you're curious about that, and if you're skeptical, I encourage you to read this. Okay, and what we're going to build today is a LocalStack extension. So extensions are a mechanism that we introduced a few months ago. As I said, LocalStack at its core is just is this AWS emulator, but LocalStack has a lot of tooling around that. So an example is you could mount if you're developing AWS Lambda, you can mount your code locally into LocalStack, so that when you change the code in your Lambda, you don't need to redeploy your Lambda. You can just update the code and run the Lambda again, and it will pick up those changes. So LocalStack provides sort of a platform with different types of developer tools that I don't have time to go into, to create this platform for local cloud development. And we're opening up that platform, and extensions are part of that. So with extensions, you can now hook into particular aspects of LocalStack, customize it, add your custom logic to add additional functionality to LocalStack. And this is what we'll do. So today, and maybe just briefly explain how extensions work. So as I said, LocalStack exposes this one entry point, 4566, where all of your AWS client software sends their AWS requests to. So whether using Terraform or AWS CLI or any type of the Java SDK or any type of AWS SDK, they will all send their requests there. And we have some internal server-side logic that parses the request, interprets which service and which operation the request belongs to, and then dispatches it to our service providers, which are these implementations of the emulated services. And we've placed extension points inside our platform. And what you can do now is you can write a Python program that where you can write code that hooks into these particular extension points. So for example, you can run code when LocalStack starts to start your own custom emulator services, for example. So we have an extension that starts a emulated Stripe API. So it's this payment provider API. Or you could add custom logic that intercepts AWS requests coming into LocalStack to, inspect them, manipulate them, or log them, which is what we're going to do. So you can find more info about extensions and how they work in our extensions repository. Right, I forgot to mention this. So extensions live on your host, and they get mounted into the container so that they survive LocalStack runs. So LocalStack itself is an ephemeral environment. It gets destroyed and recreated every time, and extensions live on your host and get mounted into the container. Okay, so what we're going to build today is we're going to create an extension that logs each AWS API call into Tinybird. So the extension will extend the response handlers, and I'll get into what that means in a minute, to intercept the request as well as the response coming back from our emulated services. And then we'll log the result into Tinybird, which will then give you lots of ways to analyze the usage of AWS of your application. So since your application behaves when it runs against LocalStack in the same way as AWS, basically this will give you a way to look inside what your application is doing with AWS. And then we'll write some queries on top of that, and Jordi will show you some functionality of Tinybird, like materialized views and aggregations on top of that data. Okay, so we have a repository. I'm sure that it's hosted by Tinybird, and all of the code that we'll show you today is in that repository. It also explains how you can set up extensions, LocalStack extensions, and how to bootstrap a new extension in the same way that I did. Okay, so I think I'm ready to rumble here. Jordi, you're still with me?
Yeah, I'm listening.
Okay. So in our, just gonna close these slides for a second here, and I'll show you the extensions repository. So the LocalStack CLI provides a tool for working with extensions, installing and uninstalling them, and also developer tooling. So if you're developing extensions, the CLI gives you ways to create a new extension, enable developer mode for them, so that when you start LocalStack, the extensions will be mounted into the container and everything. And this is all explained in our extensions repository documentation. Extensions are a LocalStack Pro feature. So if you're interested in using them, you can go in app.localstack.cloud and sign up there for a free trial period. And once you have your account, you can use the CLI to log into your account. To run LocalStack login, log in with your credentials, and then you'll get access to the LocalStack Pro commands, which includes the extensions command and the developer tools for extensions. Okay, so basically the process is to bootstrap a new extension. You run a LocalStack extension dev new, and that gives you a wizard where you can create and bootstrap a new extension. It'll create a Python distribution for you, so it create all of the necessary project files that are needed for LocalStack to pick up the distributed extension. What you then do is you enable developer mode for this newly created extension, and then there's a particular mode that you need to start LocalStack in to start these extensions that are enabled for developer mode. So I've prepared all of this already because it takes a while to set this up. And here's my sort of bare bone extension. You can see my the scaffold creates sort of a bare bone setup config. If you're familiar with Python applications, this is the way that Python declares distribution information. And it creates a make file for you with some make targets, so you can install all of the dependencies necessary for building the extensions and so forth. I think what's more interesting is to just focus on the code, and then focus also on just the tiny how easy it is to get data into Tinybird. So I have my bare bone extension here. This is my Tinybird logger extensions that extends from our base extension, which is sort of the base class for extensions living in our extensions API. If you have all of this set up in your IDE, you'll be able to browse the code and the API documentation for the extensions and everything we expose as part of the public API. But basically, what we want to do is, as I mentioned, we want to intercept each AWS API call and send that to Tinybird. So the first thing I'm going to do is I'm going to see what methods there are to override from the extension. So what we want to add is a response handler. So I don't have time to go into the details, and not that interesting. Basically, a request that comes into LocalStack goes through a set of request handlers, is then dispatched to our emulated services, and then goes through a set of response handlers that allow you to either manipulate the response or, as I said, intercept and log it. So that's what we want to do. So we want to extend these list of response handlers with our own handler, and the handler is just a function. All this AWS log AWS API call, and let's create this function here. So the signature of these handlers is you get the handler chain. It's not so important. This is the construct that executes, that's responsible for running all of these handlers. You get the request context. This indeed is an important concept that we'll get into in a second. You also get the HTTP response that's being created by the backend. And the request context contains all sorts of metadata about the incoming request. So if you run AWS S3 create bucket, for example, this service metadata will contain the name of the service, which will be S3. You can access the type of operation. So in this case, this would be in the example create bucket, and there's a bunch of other metadata. So what we want to do is just extract these metadata from the context into a payload that will later arrive in Tinybird. So let's get the service, let's get the operation, and And let's maybe get the status code from the HTTP response. So let's say you're trying to delete the bucket that doesn't exist, and the status code from the backend will be 404. Okay, so now basically that's sort of a very simple, just some extraction of metadata from this response or request. And what I'm going to do now is I'm just going to open up Tinybird, our Tinybird workspace here. And what I like about Tinybird personally is just that it gives you this easy way of incrementally developing stuff. So the first thing we want is we want to create a new data source where all of this data will go into. And so I want to use the events endpoint, which basically just gives you a way to pump JSON data into this data source. And actually, what's nice about this UI is that it already gives you like example code to work with. So here you can see some Python code that just serializes some example data into JSON and then uses the requests library to post the data to the events endpoint. And actually, what we're going to do is I'm just going to copy this piece of code here. Is this here? I'm just going to remove this token because I have my real token here in this configuration variable. And we're just going to replace this sample data with the payload that I just created. Okay, and also print the response that comes back from the from Tinybird. Okay, good. So we're extracting this payload, some metadata, serializing that into JSON, and then sending that to the events endpoint. I'm just going to rename this to AWS API calls. This will be the name of the data source. And I'm just going to start LocalStack here now for a second with this extension dev mode set to 1. So sorry, I just need to set my API key so it starts LocalStack Pro. Still running. So you see this log output informing me that extension developer mode is enabled, and it's mounting this this extension that we created into the container. Okay, so I can already see I did some mistake here in the extension that I'm going to try to remedy. So actually, not every request in that goes into LocalStack will have a service, an AWS service associated with it. So we maybe only want to log those requests where the parser has already parsed the AWS response. If this is if this is not set, then we just skip the logging of this request. That's right. All right, so let's give this a go. Let's just run, I don't know, list queues, for example. You can see the LocalStack logs the AWS request that's being executed to log output, and this is the output from that comes from Tinybird. So let's look into our workspace. And it's created this data source for us with these 3 columns, and you can see the first request landing in there already. Okay, so maybe that's not too interesting. Maybe there's a few other things that we also want to add. So one thing is definitely like a timestamp. So let's just use the current UTC timestamp with let's say seconds. And maybe we also want to add a unique session ID. So when you start up LocalStack, create a new session ID that identifies this particular LocalStack run and add that to the payload, so we can we know which AWS requests belong to one session, LocalStack session. And you can do that. Let's just declare a variable up here. And let's override its onExtension load method, which will be executed by LocalStack once when the extension load. And we'll just create a random UUID here. So let's add that to the payload as well. And what's nice about the developer mode of extensions is you can just modify your extension, run LocalStack again, and it will pick up those changes. Okay, so we added these additional fields that will now be columns in the data source. Here, and let's see what happens in Tinybird. Okay. So Tinybird is informing me that there's 2 new columns detected. I can view these 2 columns. It determines the type, guesses the types based on the input. So I'm just going to save this, and you can see that it's not actually adding because we didn't have the columns as we made the request, the data is not coming in. But if we let's run this, just the same command again. If we refresh this, we should be able to see this additional data coming in. Okay, cool. So we have the timestamp, we have the session ID in here now, and it's going to be interesting to add a bunch of other information as well. So, for example, you can get the entire parse request from the context. It's in the service request. This is a dictionary describing the parameters of the incoming AWS request. So if you run S3 create bucket, for example, this will be a dictionary that contains the bucket name and whatever other attributes you pass to the AWS API call. So basically, we just want to store the verbatim request here, and we're gonna just dump that to JSON. I'm just going to do this conceptually. I'm going to take a shortcut in a second. I've prepared like some more interesting aspects of the request context that we extract into the payload. And actually, I'm just going to do this now. So I'm going to copy this code over here and just walk you through the things that I'm extracting from from the AWS request. So we're getting, as I said, the timestamp, the session ID, the service, and the operation. You also get the region the request is made to. So the AWS region, you can get anything from the HTTP request. So in this case, the user agent, which SDK or which client is making the API call, and we're setting the request and the raw response, or sorry, rather the AWS response coming back from the backend, also into the payload. And if an error occurs, we're also going to store the type of the error and the error message. Okay, so I'm going to do the same thing again. I'm going to restart LocalStack here. And maybe delete the bucket that doesn't exist. To raise an error. And let's see what happens in Tinybird. So it's detecting all of these new columns, which is great. I'm just going to save those and do the same thing again. So just run the command again to see the data arrive. Okay, so we can see the AWS CLI is actually executing a list objects v2 operation to determine whether the bucket exists. And you can see here the incoming request dictionary there's no output, but there's an error that occurred, which is a no such bucket error, and you can see the message here. Okay, and last thing that I want to show you, and then we can get into some of the Tinybird stuff, is just what it looks like when Terraform makes a bunch of AWS requests. So just going to run Terraform apply on this configuration again. You remember this is this S3 SQS notification application. And you can see in LocalStack already, there's a bunch of these log outputs that log all of these AWS operations. If we look at the API calls, you can see all of this data arriving. Okay. Okay, so now you have all of this log data in Tinybird. So let's do something interesting with it. I'm just going to run a few simple examples on top of the data, and then Jordi will show you some advanced functionality of Tinybird just to showcase you what you can do with Tinybird on top of this data. All right, so I'm just going to create a new pipe here. And select from the AWS API calls. And what I may be interested in is just going to open up my cheat sheet here. Is that we have all these queries and everything prepared for you in our repository. Actually, I have these here. So let's say we want a total number of sessions, for example. So it's a classic SQL. You just want to select count distinct session E, from this table over here. So this is the total number of LocalStack sessions where you have data from. So if I run restart LocalStack, run another set of commands, able to see this number go up. Okay, so run this again, you can see this number going up. And maybe we want to create a time series. So let's use the timestamp field of the data. And this number of sessions. And let's group this by date. So this is just an artifact from from the data not having the timestamp column before we started adding data. So this would obviously be when you create the data source properly from scratch, and you make this a required field, you won't have these artifacts. Okay, so now you could with this query you could start tracking your team's usage of LocalStack, for example. So we know, for example, just a short digression, we know of companies who have team of 200 engineers who have dedicated teams working on developer productivity, and they use LocalStack. So they observe and monitor the use of LocalStack inside their organization, and understanding the adoption of LocalStack can be very interesting to them. So seeing the usage increase of the usage of LocalStack increase over time can be a good indicator for them. So this would be one of the queries that would facilitate this type of research. So I have another query here. I'm just going to paste in here. Basically, we want to find the most, let's say the service operation that's being called the most. So what we're going to do is we're just going to group by service and operation, and then just count the number of distinct session IDs that use that particular service and operation. So actually, this is these are sort of the let's say the most popular service operations, and we could say maybe order by number. Oops, what I did there? Number of sessions. So you saw that I was doing SQS create queue in two of the sessions. So some interesting insights to understand like which API calls your applications are making. If your application evolves and or your team is using new services, you can sort of observe the adoption of services and particular service operations in this way. Right, and what's interesting also is now that we're storing sort of the full payload of an AWS request, let's select from the AWS calls where the service equals S3. And if we look at the request object, you can see that it often contains a JSON document, as we said earlier, and we can maybe extract the bucket name from these requests. So let's just, oops, sorry. So let's get the timestamp, let's get the operation, and let's extract from the request documents the bucket name. And you can see to which bucket this particular S3 operation is made to. We only used your bucket name, but you would maybe others would show up. All right, so these are just some example queries that you can run on top of the data. As I said, if you imagine 200 engineers using LocalStack every day, and you're tracking all of this data, there's a lot of data that accumulates. And if you're interested in either asking questions about how is your team using LocalStack, and you want to write efficient queries, and what Jordi will be showing you is sort of aggregating time series and monitoring number of requests towards a particular service. In the context of LocalStack, that maybe doesn't make sense too much, but what you can think of is, if you're familiar with AWS, then you maybe know about AWS CloudTrail. So CloudTrail is an AWS internal logging mechanism that gives you basically the same data. So it gives you the service, the operation, and it gives you some basic metadata about the request and the response. So the data coming from CloudTrail will look very similar to this. And now if you sort of integrate all of that data into one Tinybird workspace, you could imagine that you can prototype these types of queries against this data, and then once you roll out your application on the real AWS and you have real production and operational data, you can run Tinybird queries on top of that to, for example, alert you when a particular service is being used more than you expect. Okay, so I think that covers my part of the demo, and happy to hand over to Jordi to show you the more advanced parts of Tinybird.
Okay, well, it's not that advanced compared with what you have done, but let's try to draw some sometimes serious data with the usage that you can get from LocalStack. As you can see here, I have a data source that we already populate for this demo. It has, I don't know how many. It has 12 million rows that we have been creating for the last. I think that since 1st of September until a couple of hours ago. So and also I have created a dashboard in Retool that is querying, it will be querying 2 endpoints that I have to create yet, and will be refreshing every 5 seconds. So let's create the first endpoint. For the first endpoint, I want to have the number of requests to one service, S3 for example, over timeline. So let's do a count. Well, first let's get the hour, for example, and then counting how many calls we are doing. Well, our team is doing to S3. So let's filter by S3 here, and we should group by timestamp, the hour. Here we will have how many calls is S3 receiving, and this should be refreshing. Maybe I put the wrong name. Check. Okay. An important step that I always forget that is I have to create an endpoint from this type. And once it's created, I guess that now it should be working. Here we have all the calls to all buckets every hour from 1st of September until today. And let's do some modifications to the query, because in the end, this could be useful, but maybe adding the bucket with the that function that already show us will be better. The bucket. And then I think that the only step missing is to group also by bucket. Now our endpoint should be returning all this data, and if we go to the indeed it's grouping by, well, let's go to the preview mode. It's returning all the data by bucket. It's a value because some operations don't have the bucket, so let's filter by bucket. And as you can see, changing an endpoint is as easy as changing the query, executing it, and you will start seeing the results. Okay, we have this now, and maybe as Thomas was saying, let's try to create another pipe where we can control what our team is doing. So maybe counting all just the request to S3. And let's try to set up some kind of alarms so we can see the hours with more requests. So I have to go by timestamp. I don't know what is wrong now. I'm missing something. Oh. Okay. Now we have,
Happens to the best of us, Jordi.
yeah. Now let's try to do some simple operation. Having here a filter, let's say any hour with more than 2,000 requests. It's an let's say it's not everything today. Now let's see. Yeah. Time I forget to create the endpoint. So it's that easy that you always forget to do it.
Yeah, that's true. But you get the confetti, you get the dopamine from the confetti.
It's an important thing.
Yeah.
And now you can see that you have all the requests, and the hours with more than 10,000 are in red, showing that there is not an error, but an alarm or something that you have to review this day. We can make it more complicated. Maybe we can try to make this dynamic. And what I can use here, let's try to get the average of the last 12 hours and the standard deviation, and do some basic computation to set a dynamic alarm, let's say. I've already written the windows because, they are not that difficult to write, but there are a lot of things to remember. So let's do it this way. Now set the filter as the mean, and let's put 3 times the standard deviation, and same as before. And this is the status from, and we should do the trick. Well, I put it here in the same node, but in Tinybird you can use nodes as subqueries. So here it will be as easy as, sorry, querying the previous node.
Is there anything I need to consider performance-wise when using additional nodes, or is Tinybird just doing a magic for me?
Yeah, it does the magic for you. I mean, in the end, we compose everything into a single query. So the previous query is equivalent to the one being executed if I create an endpoint from here.
It's a simple idea, but it gives you this nice sort of. I used Jupyter notebooks a lot when I was doing research, and this feels very much like that because you have this intermediary steps, and it's nice to know that you can use it in the same way. Not worry about performance.
Yeah, that's. I mean, in this example, maybe it's too simple, and in the end, you can see here the mean and the standard deviation. But maybe if you want to return in the endpoint just the timestamp and the count, you don't have to have the mean and the standard deviation here, and you can debug the intermediate step here easily. It's quite easy. And then let's create the endpoint from this node now. And this now is more flexible. I mean, this point here and this one here was not being shown as an alarm before because we were considering just the request bigger than 10,000. But now let's go to the important thing here, because these queries are working fine and we are returning what we are expecting. But for example, this endpoint is consuming, well, let's say reading 200 megabytes every time that it's being called, and the other one is reading 1.6 gigabytes. So queries are performing okay. To 200 milliseconds, it's a good response time, but I think that we are consuming we are reading too many bytes. So let's create a materialized view. Let's call it the API calls. And since we're almost running out of time, let me copy it from another place. Okay. Let's not filter the empty buckets.
So the JSON extract is reasonably expensive, right? So is that the particular thing that we want to get rid of?
Well, not just the JSON extract, but also in the end, the JSON extract is parsing a JSON, but as you have shown us, it's not that big. It's just 2 fields. But when we are querying by service, let's see here. Yeah, we are querying. We don't have here in the sorting key the service, for example. So it will be better if we have it, or in this case, we are filtering it. So we don't need it. But for example, we don't have the bucket in the sorting key because it's a JSON file field. So let's create and also when you do a materialized view, in this case grouping by hour, you will reduce, you will aggregate the data by hour. In the other data source, in the big one, you have every event by itself. So it will behave better if we create a materialized view. And I think that's everything that we need to do. Let's run the query, create the materialized view. We just need to give a name to the data source. And this is the default sorting keys and the default order based on the group that we are doing. And the partition key, I think that it's okay to have mount here, at least for the demo purposes. And let's populate everything with the historical data. And this will take a few seconds.
I already prepared the extension, so it actually sends the data to the new data source, to this historic data source. So it'll be interesting to see whether the demo gods are on our side, and if we query this materialized view, we can actually see new buckets arriving. I'll come up with some creative bucket names.
Great. Let's modify the API endpoints. We change. We have here now the state. The timestamp is already compute. And I think that, we don't need to filter by service. This one should be working already. Let's check the dashboard. Yep. Let's see how the processes data has changed. Yeah, as you can see here, we went from 200 megabytes to 30 kilobytes.
That's awesome.
And response time is also going down to 14 milliseconds.
So when I add new data to the underlying data source, how quickly does the data arrive in this new materialized view?
It should be there in few seconds, if not milliseconds. But you are adding new buckets?
Yeah, can you maybe, so we won't see this here because I'm not generating that amount of data, but can we just query the materialized view that you just created? Can you create a new pipe on top of that?
Yeah. Well, let's fix also this one, and then we can do what you are suggesting.
Yeah, that would be awesome. Yeah, so we can just see an order by timestamp and just see the new buckets arrive.
Yeah. I want to fix this one because it's the one consuming 2 gigabytes. Okay. Now if we start doing calls, okay, now we can see that we went from 1.6 gigabyte to 60 kilobytes. Okay.
That's great.
And then you want to check what we are receiving in this one.
Yeah, just want to see curious to see how fast the data arrives through this materialization. So you're ordering by timestamp now?
Yeah.
Let's see if I'm actually doing this correctly.
Yeah. I see a new bucket.
Awesome. This is like I'm just in this. So there's barely any latency. So this is cool. So you can really see the pipelines working at really low latency.
Yeah. That's all. I don't know if we have any. Well, I don't know if you want to add something else, Thomas. If not, we can check the chat and see if we have any questions there.
Yeah, happy to answer any questions that people may have. This was fun. It's as I said, we're using Tinybird internally at LocalStack to on the one hand, we have a data product that we serve to LocalStack users. So some of the aggregations that we showed today are actually provided to you as a user when you use LocalStack Pro. So you can start inspecting. Actually, we're rolling out a new feature for that in a couple of weeks, where you'll then, we call it Stack Insights. So you can click on your LocalStack run and then get some aggregated data over over your LocalStack runs. So you can inspect your own usage, and the backend is actually served by Tinybird. And we also use Tinybird for our data warehouse for business data, and it's been super helpful. Sometimes you make some naive queries that don't process too much data, or the data sources aren't that big, but then it turns out to just one query run takes gigabytes of data, and then you need to just rework that with materialized views. But it's been really pleasant experience using it.
Yeah, the good thing about what you said is that even if when you are querying few gigabytes of data, the queries are fast enough to check what's going on, and if it makes sense to do a materialized view, or to try to play with the sorting keys.
Yeah.
Well, to do some performance analysis and see what can you improve.
Yeah.
Okay, looks like we don't have any question in the chat. I guess that everything is clear.
Everything is clear, yeah. or too much information. We'll see. Maybe questions will arrive in the upcoming days when people watch the recording of the stream.
Yeah, for sure.
Yeah. Okay, well, I guess this concludes the stream. Thanks for hosting me, Cordy. This was fun.
Thank you, Thomas.
Hope to see you soon again.
See you soon. Bye.
Bye.